Exponents. So the first thing I want to look at is what happens when you take a number and you raise it to the 0 power. Well, here it is right here. It equals 1. But that seems a little strange, right? So let's look at why that is. So let's look at the powers of 2, because those are familiar numbers. We deal with them all the time. So let's say I'm going to write 2 to the 4th and 2 to the 3rd and 2 to the 2nd and 2 to the 1st and 2 to the 0. So going backwards, 2 to the 4th, we've got 2 times 2, 4, times 2, 8, times 2, 16. Right? I'm just going to fill the rest of them in. 2 to the 3rd is 8, 2 to the 2nd is 4, 2 to the 1st is 2, and let's not fill this one in just yet. But what I want you to look at is the pattern. If we start with 16 and we go down, right, decreasing, we can see that we divide by 2 to get to the next number in the pattern of powers of 2. If I keep doing that, again, I divide by 2. 8 divided by 2 is 4. Keep doing that, divide by 2. Keep doing that pattern. There's no reason to think that that pattern's going to change, right? It's going to stay the same. So 2 divided by 2 gives us 1. And that will work regardless of which number you're raising to the 0 power. It will always be 1. Now, I could keep going, right? Like, what if I get into negatives, which we're not going to get too much into right now, but the pattern does keep going. So if I divide by 2 again, 1 divided by 2 is a half. Yes, we're going to start getting into fractions when we have negative exponents. But for now, what I want you to focus on for this slide is that any number to the 0 power equals 1. You can say it over and over if it helps you remember it, but anything to the 0 is 1. Anything to the 0 is 1. All right, let's take a little deeper dive into exponents. So here I've got some exponents written out, right? So the first one, x times x. Well, x times x is going to be x to the 2nd. And if I have 3 x's now that I'm multiplying all together, x to the 3rd. 4 x's, 5 x's, 6 x's, right? We know this. We've written this out before, right? You multiply a number or a term or a variable by itself, and the number of times that that variable appears in the multiplication problem is equal to the exponent, right? So 3 x's means x to the 3rd. So let's look what happens when we use this to multiply powers of x. So to multiply powers with the same base, add the exponents, and we're going to see what that looks like. So if I look at even just x times x, right? If there's no exponent, then the exponent that's actually there is a 1. So this is x to the 1st times x to the 1st. And we know that x times x is x to the 2nd, right? We just looked at that because x times x, right? But another way we can now look at this is by looking at the exponents and adding them together, right? We see it with numbers too. I mean, it's not just with variables, right? It works with, it's not just with variables, it works with numbers, right? We could write this as 3 to the 1st times 3 to the 1st, which equals 3 to the 2nd, which we know is 9. And again, 1 plus 1 will give us 2. So let's try this. I have a few examples for you with variables. Now, again, these could easily be numbers, right? Instead of x, it could be a 3 or a 2 or a 1 or any number that I pick, right? So if I want to know what this equals, I know from looking at the rule that I have to add the exponents, but let me just show you why. So if I have x to the second times x to the first, think about what that would look like. Here's x to the second, right? And here's x to the first. All together, I've got 3 of them. On this one, 5 x's, right? X to the 5th means 1, 2, 3, 4, 5. And then x to the 3rd means I've got 1, 2, 3. But when I count them all up, I've got 8. This last one, I'm not going to write this one out. I'm just going to trust what I would get, right, which is 3 x's and 2 x's, and add those exponents together to get x to the 5th. All right, a little bit harder now. Not really, but it looks a little bit more complicated. I can only multiply when the bases are the same. So I could use the commutative property of multiplication to write these in a different order. And I'm going to write an exponent on the one that just has an x, because I know that this little term right here is really x to the first. So I'm going to write x to the first, x to the 3rd, right? I'm putting my 2 x terms together, and then I'm going to put my 2 y terms together. Now you might be looking at this going, but there's nothing in between. Like, what are we doing when they're all just smushed together like that? That implies multiplication. So if we're multiplying these together, we can only multiply the ones that have the same base. So I'm going to multiply these first, and to do that, add the exponents. And then I'm going to multiply these. And again, to do that, add the exponents. And we're done. All right, take a look at this one. Same thing, I can only multiply if they have the same base. So to multiply these together, I'm going to add the exponents. And then I've got my y terms here, and remember, y means y to the first. So I've got 2 plus 1. That's it. This is my final answer. This is my final answer. I can't multiply the x and y together. I mean, I can. This is what it looks like. But I can't simplify any further. This is as far as I can go. Now let's take a look at division. So in this first example, any number over itself, like, for example, if I have, let's say, 3 over 3, any number divided by itself, we know, is 1. So x divided by x is no different, right? Because that represents a number. So every time I have x over x, that's just going to equal 1, right? And what exponent should I put for it to equal 1? Think about that. X to the what power equals 1? I'm hoping you're thinking 0, right? Because anything to the 0 power is 1. All right, let's look at this next one. Here, I've got x to the second on top, and I've got x to the first on the bottom. But remember, anytime I have an x over an x, that's equal to 1, right? So these cancel out, and then I'm just left with x to the first, right? Because I've just got this lonely little guy up here. Again, anytime x over x, that cancels out, right? But let me write what we've got. We've got x to the 4th on top, and we've got x to the 2nd on the bottom. I can cancel these because x divided by x is 1. X divided by x is 1. And, you know, when we multiply by 1, it doesn't do anything, right? It's called the multiplicative identity, because when you multiply by 1, it doesn't change the answer. So what I've got left here are these 2 little x's over here, so x to the 2nd. Let's look at this one. 1, 2, 3, 4, 5 on top, and 2 on the bottom. So if I cancel these out, I'm left with just the 3 on top. And then the last one we've got here, there are 5 x's again on top and 1 on the bottom. So I cancel that pair and I've got 4 left on top. Right? So I want you to look for a pattern with me just for a moment. So here, my numbers for my exponents were 4 and 2, and my final exponent was 2. Here, my numbers were 5 and 2, and the answer, well, the exponent in my answer was 3. Here, I've got a 5 and a 1, and my final answer was x to the 4th. Notice anything? Hopefully you're thinking, yeah, I see a pattern there. And here it is. To divide powers with the same base, we subtract the exponents. So like we saw with x to the 1st over x to the 1st, right? 1 minus 1 is 0. So we get x to the 0, which equals 1. But we knew that x over x is 1, right? This just shows how the property works whenever it's applied with division. Here we've got 27 over 3. Now we know the answer to that is 9, right? 27 divided by 3. But let me write it in powers of 3. We have 27 is 3 to the 3rd, and 3 is 3 to the 1st, and 3 minus 1, 3 to the 2nd, which is 9, right? So yes, this was a long way to go about getting 9, but I'm not saying that you should do that method when you're dividing 27 by 3. I'm just trying to show you that it works wherever you're dividing powers that have the same base. So let's try a few. So for this one, we've got x to the 3rd divided by x. Now for this first one, I'm going to write it out. So I've got x times x times x over x. You can also think of it in terms of like where I've got a pair and where I would have some left over, right? Because if I cross these two out, I've got 2 x's left on top, so that would be x to the 2nd. Just another way to think about it if you're more visual like me. All right, here, I could write it out. Actually, I'll do this last one. I said I was just going to do that one, but I'll write this one out too. So I've got 5 x's on top, and I've only got 2 x's on the bottom. These cancel, and I'm left with x to the 3rd on top. Now I could have just as easily done 3 minus 1 to get 2, or 5 minus 2 to get 3, which is exactly what I'm going to do on the next problem. So 7 minus 6 equals 1, or I could just write x. Let's try one more. Just like we could only multiply with the same base, we can only divide if the bases are the same too. So if I'm going to divide these, I'm going to subtract the exponents. 3 minus 2 gives me 1. And then I'm going to do the same thing with the y's. This is y to the 1st, remember. 5 minus 1 is 4. And remember, this works with numbers as well.